In this video, we will look at basic transformations of graphs. That is, if we change the equation of a graph slightly by either addition, subtraction, multiplication, and division to either x or y values, how the shape of the graph will change accordingly. Specifically, we are looking at changes that do not change the fundamental shapes of the graphs. These changes can be in the form of translations, which means to move the graphs in its entirety in either the x or y directions. So for example, I may have a graph that looks like this initially. I am free to move it left, right, so I'll end up with a graph that looks something like this after I translate it to the right, or I can translate it to the left and I'll end up with something like this, or I can shift the graph up or down. Maybe I can shift it up now and I'll end up with this graph, and I can also shift it downwards to end up with a graph like this. All this belongs to translation because I'm simply shifting the graphs around without changing its shape at all. We can also scale a graph. Scaling means to either stretch or compress a graph. So we can either make a graph taller, shorter, fatter, or thinner. These operations do not change the fundamental shapes of the graphs, but the size of the graph will be affected. So for example, if I have a graph like this, I can choose to stretch it vertically to end up with a graph that looks like this. I can also choose to compress it vertically, which ends up with a graph like this. Or I can also choose to stretch it horizontally. So if I have a graph that looks like this, and after stretching, it will look something like this. For compression, it will become thinner, so it becomes something like this. Finally, we can also reflect any graphs about either the x or the y axis. So for example, if I have the same graph, I can reflect it about the x-axis to end up with something like this, or I can reflect it about the y-axis and I will end up with a graph that looks like this, where every point has been reflected. Let us now take a look at the individual transformations in more details. For transformations that take the form of y equals to fx plus a, it is representative of a translation parallel to the y-axis, because every fx or y value is now increased or decreased by a constant value of a. So if a is a positive value, what happens is all y values are going to be larger now, and thus this results in a graph with larger y values, and it is going to shift the graph upwards. We describe this transformation as a translation in the positive y direction by a number of units. So there are three components in how we describe this transformation. Number one, what kind of transformation it is. Is it a translation or a scale? Number two, the direction at which this transformation is occurring, in the x direction or in the y direction, or in the negative x direction or negative y direction. And number three, the magnitude of this transformation. How large or how small do we transform this graph? That depends on the number of units that we are going to transform. Similarly, if we have a negative value of a, we will translate the graph in the negative y direction by a units. In example 1a, we are given the graph of y equals to fx and are asked to sketch the graph of y equals to fx plus 2. We know that this is equivalent to a translation of the graph in the positive y direction by 2 units. So we simply have to draw the same blue curve but higher, and thus we will end up with this red curve. Do note that if we know the original coordinates of any points, we have to include the transform coordinates of these points as well, like this. And also, if we know any equations of asymptotes, we will have to write down the equation of the transform asymptotes as well. If instead we are asked to sketch the graph of y equals to fx minus 3, we will redraw the entire blue curve 3 units lower, and thus end up with this red curve. Next, if we have an addition of a constant within the bracket of y equals to fx, this changes the x values rather than the y values, and thus this shifts the graphs parallel to the x-axis. However, do note that the sign here is opposite as that of the translation in the y direction. In fact, you can remember that regardless of whether it is translation or scaling, which we will cover later, the effect on x and on fx are always going to be opposite. If we have a positive value of a, we will translate the graph in the negative x direction, and if we have a negative value of a, we will translate the graph in the positive x direction. In example 2a, we are asked to sketch the graph of y equals to f of x minus 2. This is a translation in the positive x direction by 2 units. Hence, we will sketch the same blue curve but 2 units to the right, and we will end up with this red curve. For the graph of y equals to f of x plus 4, this represents a translation of 4 units in the negative x direction. Thus, we will sketch the same blue curve but 4 units to the left and arrive at this red curve. Following translations, we will now look at the scaling of graphs. If we multiply fx by a constant value of a, where a is a positive real number, what we are doing is multiplying all y values by a factor of a. This is not a constant increase or decrease in the value of y, but instead, the larger the magnitude of fx, the larger the effect of the multiplication. Thus, points nearer to the x-axis experience smaller amounts of change as compared to points further from the x-axis. This causes a stretch parallel to the y-axis if the value of a is larger than 1, and a compression parallel to the y-axis if the value of a is less than 1. We will look at negative values of a at a later time. In example 3a, we will sketch the graph of y equals to 2 times of fx given y equals to fx. So we know that this is a scaling parallel to the y-axis with a factor of 2. All y values of the graph will be multiplied by 2, and we end up with the red curve like this. If instead we are asked to sketch the graph of y equals to half times of fx, all y values will be multiplied by half, and thus the graph becomes shorter, giving us this red curve. If instead the multiple a is not placed within the bracket, it affects the x values instead of y values, and this results in scaling parallel to the x-axis. As mentioned earlier, the effects are opposite to what we have learned for the scaling parallel to the y-axis. When we have y equals to f of ax, we divide all x values by a instead of multiplying them by a. When a is more than 1, the graph is compressed. When a is between 0 and 1, the graph will be stretched instead. Now, given this cubic graph y equals to fx, y equals to f of 2x results in a scaling parallel to the x-axis by a factor of half, which means that we get a thinner graph after transformation, which looks like this. If instead we are asked to sketch the graph of y equals to f of half x, we will get a fatter graph as all x values are divided by half, which is equivalent to multiplying by 2. Thus, we will end up with this graph. Finally, we look at reflections of graphs about the axis. If instead of a positive constant, we multiply fx by negative 1, this results in a reflection of the graph about the x-axis, since all y values experience a change in sign when we multiply them by minus 1. So, all the positive y values become negative, and all the negative values become positive. In example 5, we are now asked to sketch the graph of y equals to negative fx, which is a reflection about the x-axis. So what we have to do is to simply flip the graph upside down, and we will end up with this red curve. If the negative sign is instead applied within the bracket, all x values will have their signs changed, and thus this results in a reflection about the y-axis. We can thus obtain the graph of y equals to f of negative x very easily by flipping the graph right side left instead of upside down. Thus, this gives us the red curve.